Black holes, the place where the universe breaks. The point of no return. Imagine traveling through space toward an object so massive that even light cannot escape it. At first, everything appears normal. Stars shine in the distance. Your spacecraft moves silently through the darkness. But ahead of you is something strange. A region of space with no surface, no visible walls, and no obvious entrance. Yet once you cross a certain invisible boundary, there is no turning back. That boundary is called the event horizon. And here's where the mystery begins. From your perspective, you might cross it without encountering a physical wall or sudden explosion. But to a distant observer watching you from far away, something extraordinary appears to happen. Your movements seem to slow. Your light becomes increasingly red. And as you approach the event horizon, you appear to fade into darkness. But did you actually stop? Or did you continue falling into a place from which the rest of the universe can never receive your message? Scientists have spent decades trying to understand what happens beyond that boundary. Because deep inside a black hole, our current understanding of physics reaches its limits. And at the center may be something even stranger, a singularity. A place where our equations suggest that matter could be compressed to an extreme state and space-time itself becomes profoundly distorted. But there's a problem. Our theories of gravity and quantum mechanics don't fully agree about what should happen there. So perhaps the most terrifying question isn't, what happens when you enter a black hole? It's this, what happens to reality itself? And to answer that, we need to begin at the moment a black hole is born. How is a black hole born? A black hole doesn't simply appear in space. In many cases, its story begins with a star. A massive star can spend millions of years fighting an invisible battle. Gravity constantly tries to crush the star inward. But deep inside the star, nuclear fusion produces enormous energy pushing outward. For most of the star's life, these two forces balance each other. Then the fuel begins to run out. The outward pressure weakens, and gravity finally gets the advantage. The star's core begins collapsing at incredible speed. In a massive enough star, this collapse can trigger a supernova, one of the most powerful explosions in the universe. But the explosion isn't necessarily the end. The remaining core can continue collapsing under its own gravity. It becomes smaller and smaller and smaller. The gravitational field becomes so intense that eventually a boundary forms around the collapsing object, the event horizon. Once that happens, anything that crosses it, including light, cannot escape back into the outside universe. A black hole has been born. But here's something important. The black hole isn't an empty hole in space. It is a region where matter has collapsed into an incredibly compact state, creating an extreme distortion of space-time. And the more massive the black hole becomes, the larger its event horizon can become. Some black holes have only a few times the mass of our Sun. Others are millions or even billions of times more massive than the Sun, sitting at the centers of galaxies. And that's where the mystery becomes even deeper. Because if black holes can grow to such enormous sizes, what happens when you get too close to one? What would you see? What would happen to time? And could you survive crossing the event horizon? The event horizon, the point of no return. Imagine you're approaching a black hole. From far away, it doesn't necessarily look like a giant cosmic vacuum cleaner. The black hole itself is dark because no light can escape from within its event horizon. But around it, things can become spectacular. Gas and dust can spiral inward at enormous speeds, forming a glowing accretion disk. Friction and extreme gravitational forces can heat this material to incredible temperatures. And somewhere within this violent environment is an invisible boundary. The event horizon. It isn't a solid surface. There is no wall, no barrier, no warning sign. If you were falling toward a sufficiently large black hole, you might not notice the exact moment you crossed it. But crossing that boundary changes everything. Before the event horizon, escape is still theoretically possible. You could fire your engines and move away. But once you cross it, every possible future path leads deeper into the black hole. Even a beam of light cannot find a route back out. And this creates one of the strangest effects in the universe. What happens to time? To someone watching you from far away, your clock appears to run increasingly slowly as you approach the event horizon. The light coming from your spacecraft becomes increasingly redshifted and dim. Eventually, you become almost impossible to see. But from your own perspective, assuming the black hole is large enough and the surrounding environment doesn't destroy you first, your clock continues ticking normally. You cross the event horizon, and you don't see yourself frozen there. You continue falling. This difference between what you experience and what a distant observer sees is one of the most fascinating consequences of Einstein's theory of relativity. But there's an even stranger question. If you can cross the event horizon without seeing a physical barrier, what happens after you cross it? Could you somehow turn around? Could you send a message back? Could you use an incredibly powerful engine to escape? Unfortunately, according to our current understanding of general relativity, no. Inside the event horizon, escaping isn't simply a matter of having a powerful enough engine. The structure of space-time itself has changed, and every future-directed path leads toward the black hole's interior. So the event horizon isn't merely a place where gravity becomes strong. It's a boundary separating two radically different possibilities. Outside, escape is possible. Inside, escape is no longer part of your future. And now we reach the terrifying part. Because, as you continue falling, the gravitational difference between different parts of your body can become enormous. Your feet could experience a significantly stronger gravitational pull than your head. You would begin to stretch and stretch and stretch. Scientists have a name for this bizarre process: spaghettification, and it may be one of the strangest ways matter can be destroyed in the universe. Spaghettification, when gravity tears you apart. Imagine you're falling toward a black hole. At first, you might not feel anything unusual, but as you get closer, something terrifying begins to happen. The black hole's gravity is not equally strong everywhere. The closer you are to the black hole, the stronger the gravitational pull. So if your feet are closer to the black hole than your head, gravity pulls much more strongly on your feet. That difference is called a tidal force. And near a small black hole, those tidal forces can become enormous. Your body begins to stretch vertically while being compressed from the sides. You would be pulled longer and thinner, like a strand of spaghetti. That's why scientists call the process spaghettification. But here's something fascinating. The size of the black hole matters. If you approached a relatively small stellar mass black hole, the tidal forces near its event horizon could be catastrophic. You might be stretched apart before around the time you reached the event horizon. But a supermassive black hole is different. Because its event horizon can be enormous, the gravitational gradient at the horizon can actually be much weaker. That means, theoretically, you could cross the event horizon of a sufficiently massive black hole without immediately being torn apart. For a brief period, you might not even notice that you had crossed the point of no return. But your journey would still have an end. As you continued deeper toward the black hole's center, the tidal forces would eventually become extreme. Atoms, molecules, cells, and ultimately the structure of your body could be ripped apart. And then we reach the greatest mystery. What is waiting at the center? According to classical general relativity, everything eventually reaches a singularity of region, where the theory predicts space-time curvature becomes extreme and quantities such as density can diverge. But here's the problem. Physicists don't believe that this necessarily tells us the final story. The equations are telling us that our current theory has reached its limit. General relativity works extraordinarily well for gravity on large scales. Quantum mechanics works extraordinarily well for the microscopic world. But inside the deepest region of a black hole, we need a theory that can describe both gravity and quantum physics at the same time. We don't have a complete one yet, and that means the center of a black hole remains one of the greatest unsolved mysteries in modern physics. Maybe the singularity is real. Maybe quantum effects prevent it from forming. Maybe space-time has a completely different structure at that scale. We simply don't know. And that leads to an even bigger mystery, because if something falls into a black hole, where does its information go? That question created one of the most famous problems in theoretical physics. The black hole information paradox. Now we reach one of the deepest mysteries of black holes. Imagine you throw a book into a black hole. The book contains information, every letter, every page, every detail about its physical state. From the outside, however, you can't retrieve that information once the book crosses the event horizon. But maybe that's not a problem. Now we reach one of the deepest mysteries of black holes. Imagine you throw a book into a black hole. The book contains information, every letter, every page, every detail about its physical state. From the outside, however, you can't retrieve that information once the book crosses the event horizon. But maybe that's not a problem. Perhaps the information is simply trapped inside the black hole. Then, in the 1970s, something extraordinary was proposed. Black holes may not be completely black. According to Stephen Hawking's calculations, black holes should slowly emit a faint form of radiation, now known as Hawking radiation. This radiation carries energy away from the black hole. And because losing energy means losing mass, the black hole should gradually shrink. Given enough time, it could eventually evaporate. Now comes the paradox. Suppose that book fell into the black hole. The black hole eventually evaporates. The black hole is gone. The book is gone. So what happened to the information contained in the book? Did the universe simply erase it? That would create a huge problem for quantum mechanics. In ordinary quantum theory, information about a physical system is not supposed to simply vanish from existence. But if black holes destroy information permanently, then one of the fundamental principles of quantum physics could be in trouble. This became known as the black hole information paradox. For decades, physicists debated possible solutions. Maybe the information is encoded in the Hawking radiation. Maybe it remains somehow connected to the black hole's horizon. Maybe our understanding of space-time is incomplete. Or perhaps the information is preserved in a way that we don't yet know how to describe. Modern theoretical physics has made significant progress toward understanding the paradox. But there is still no universally accepted simple picture that tells us exactly what happens to every bit of information. And this mystery reveals something profound. Black holes aren't just strange objects floating in space. They sit at the intersection of gravity, quantum mechanics, information, and the nature of space-time itself. And if we eventually solve the information paradox, we may learn something much bigger than how black holes work. We may discover something fundamental about how reality itself is constructed. But there's another possibility that sounds almost impossible. What if the information doesn't simply remain inside the black hole? What if the surface of the black hole somehow stores it? What if a three-dimensional world can be completely described by information encoded on a two-dimensional boundary? This strange idea eventually became connected to one of the most revolutionary concepts in modern theoretical physics, the holographic principle, and it suggests that the universe may not be quite as three-dimensional as it appears. Is the universe a hologram? Imagine holding a hologram. It looks three-dimensional, but the information needed to create that image is encoded on a two-dimensional surface. Now imagine something far more extreme. What if the same basic idea could apply to the universe itself? This is the strange possibility behind the holographic principle. The idea emerged partly from studying black holes. Physicists discovered something surprising about black holes. Their entropy, the amount of information associated with them, appears to scale with the area of the event horizon, rather than the volume inside it. That is deeply strange. You might expect the amount of information a region can contain to depend on how much space is inside that region. But black holes suggest something different. Perhaps the fundamental information describing what happens inside a region can be represented on its boundary. Think about it this way. Imagine a gigantic room. Normally, you would expect the room's information to be stored throughout its three-dimensional volume. But the holographic principle suggests that, under certain theoretical descriptions, the same physics might instead be encoded on a lower dimensional boundary, like a cosmic hologram. But there's an important distinction. This does not mean scientists have discovered that we are literally living inside a giant computer-generated hologram. That's a popular interpretation, but it's much stronger than what the physics actually establishes. The holographic principle is a serious theoretical idea about how information and gravity may be related. And one of its most powerful realizations comes from a theory called ADS, CFT correspondence, which proposes an equivalence between a gravitational theory in a higher dimensional space and a quantum theory without gravity on its lower dimensional boundary. If something like this ultimately describes our universe, it could completely change how we think about space. Because space might not be fundamental, it might somehow emerge from information and quantum relationships. And this leads to an astonishing possibility. Maybe the universe isn't built from space first, with information placed inside it. Maybe something more fundamental exists beneath space itself. Space emerges from it. But black holes still have another secret. They don't necessarily live forever. They can slowly lose energy. They can shrink, and theoretically, they can eventually disappear. Which raises an extraordinary question. What happens during the final moments of a black hole's life? Does it vanish completely? Does something remain? Could the final stage reveal new physics that we have never seen before? Or could the black hole leave behind a mysterious remnant? The death of a black hole. For something that seems almost eternal, a black hole has a surprising weakness. It can die. According to Stephen Hawking's prediction, black holes should slowly lose energy through a quantum process known as Hawking radiation. The effect is extraordinarily weak for large black holes, so weak that a black hole formed from a massive star would take an unimaginably long time to evaporate. But the principle is fascinating. A black hole doesn't simply sit there forever. It slowly loses mass, and as it loses mass, something strange happens. The smaller it becomes, the hotter it gets. As the black hole shrinks, its Hawking radiation becomes stronger. That means the final stages could become dramatically more energetic than the beginning. Eventually, the black hole could reach an extremely tiny size, and then we encounter another major mystery. Our current theories aren't sufficient to confidently describe the very final moment. Does the black hole completely disappear? Does it explode in a final burst of radiation? Does some tiny quantum remnant remain? Or does something even stranger happen? We don't yet know, and there's another remarkable consequence. The black holes we see in today's universe are nowhere near the end of their lives. The universe is still relatively young compared with the enormous timescales involved in black hole evaporation. If the universe continues expanding for unimaginably long periods, ordinary stars will eventually disappear. galaxies will change, matter will become increasingly sparse, and black holes could eventually become some of the last major objects remaining. Imagine a universe almost completely dark, no bright stars, and eventually, even the black holes themselves may disappear. The universe could enter an era where almost nothing remains. But there is an important caveat. This is based on our current understanding of physics and cosmology. We don't know whether the universe will actually evolve exactly this way, because we still don't fully understand dark energy, quantum gravity, or the ultimate fate of the cosmos. And that uncertainty brings us to an even more bizarre possibility. What if black holes aren't simply cosmic dead ends? What if, under some hypothetical physics, the extreme conditions inside them could somehow connect to another region of space-time? Perhaps another universe. Perhaps another part of our own universe. Or perhaps nowhere at all. These ideas lead us toward one of the most mysterious objects ever proposed. The white hole, a theoretical object that would behave almost like the opposite of a black hole. Instead of allowing things to enter, but not escape, a white hole would allow things to emerge, but nothing could enter. And if black holes and white holes were somehow connected, we could be looking at something even stranger. Could a black hole be a doorway? For decades, scientists and science fiction writers have imagined a terrifying possibility. What if a black hole isn't the end of the road? What if it is an entrance? Einstein's theory of general relativity allows mathematical solutions that resemble tunnels through spacetime. These hypothetical structures are called wormholes. Imagine folding a sheet of paper so that two distant points touch. Instead of traveling across the entire sheet, you could imagine a shortcut connecting the 2 points. A wormhole would be something like that, but involving the geometry of spacetime itself. And here's where black holes enter the story. Some mathematical descriptions suggest that certain black hole solutions can be associated with a hypothetical Einstein-Rosen bridge. On paper, it can resemble a connection between different regions of spacetime. But there's a major problem. A mathematical possibility isn't the same thing as a usable tunnel. The simplest Einstein-Rosen bridge isn't traversable. It would pinch off too quickly for anything to safely pass through. And we have no observational evidence that traversable wormholes exist. Keeping one open would likely require exotic physical conditions, potentially involving forms of negative energy that we don't know how to produce or control on the required scale. So could you fly into a black hole and emerge somewhere else? With current physics, we have no evidence that you could, in fact, crossing the event horizon of an ordinary black hole doesn't give you a known route to another universe. But the mathematics raises an intriguing question. What if our understanding of black hole interiors is incomplete? Some speculative theories have proposed that the interior might connect to another region of spacetime. Others have explored the possibility of black holes giving rise to baby universes. These ideas are fascinating, but they remain speculative. There is currently no confirmed evidence that black holes are portals to other universes, and yet the possibility remains an irresistible question, because black holes already force us to accept something extraordinary. Space and time aren't fixed backgrounds. They can bend, they can stretch. They can become so distorted that our normal understanding of direction and time breaks down. And perhaps the strangest possibility is still ahead. What if our entire universe is connected to a black hole? Some theoretical models have explored whether a universe could emerge from conditions associated with gravitational collapse. That does not mean scientists have proven that our universe is inside a black hole. There is no confirmed evidence for that. But the idea demonstrates how deeply black holes challenge our assumptions about reality. Because once you start asking what lies beyond the observable universe, and what lies beyond an event horizon, you eventually reach the same fundamental question. Where does space itself come from? And that brings us to the final mystery. Not what is inside a black hole, but what black holes might be telling us about the universe itself. The ultimate black hole mystery. We've traveled from the birth of a black hole, to its event horizon, to spaghettification, to Hawking radiation, and even to the possibility of wormholes. But all of these mysteries eventually lead to one enormous question. What are black holes really telling us about reality? For more than a century, Einstein's theory of general relativity has described gravity with incredible accuracy. It tells us that massive objects curve space-time. It predicts black holes. It predicts gravitational waves. And observations have confirmed many of its extraordinary predictions. But general relativity has a limit. When we push it toward the center of a black hole, the equations eventually produce a singularity, a place where the mathematics stops giving us a physically meaningful description. At almost the same time, quantum mechanics tells us that nature behaves according to completely different rules at microscopic scales, and that's the problem. Two incredibly successful theories, one universe, but they don't completely fit together. Physicists believe there must be a deeper theory often called quantum gravity that can explain what happens when gravity becomes incredibly strong and quantum effects become unavoidable. Black holes may be the ultimate laboratory for discovering that theory, because inside them, space-time itself becomes part of the experiment. Maybe the answer will involve strings vibrating through extra dimensions. Maybe space-time is made from microscopic quantum structures. Maybe information is more fundamental than matter. Or maybe the universe has a structure so strange that our current concepts of space and time are only approximations. We simply don't know. But there's something we do know. Black holes aren't just monsters hiding in the darkness. They are clues. Clues that may point toward a deeper understanding of the universe. And humanity has already begun observing them in ways that would have seemed impossible only a few decades ago. We've detected gravitational waves produced by colliding black holes. We've observed the shadow-like structure surrounding a supermassive black hole, and every new observation gives scientists another piece of the puzzle. Yet the deepest part of the mystery remains hidden behind the event horizon. We cannot simply look inside. We cannot send a probe back out. And we cannot directly observe what happens at the center. So the ultimate black hole mystery remains. What happens to space-time when it is pushed to its absolute limit? Perhaps one day, a new theory will answer that question. And when it does, we may discover that black holes weren't breaking the laws of physics at all. They were showing us that we never understood the deepest laws in the first place. And perhaps that's what makes black holes so fascinating. They aren't merely places where light disappears. They are places where our understanding disappears, and beyond that darkness may be the next great revolution in physics. The final question: what is really inside? We have reached the edge of what modern physics can confidently explain. A black hole forms, matter collapses. An event horizon appears. Anything crossing it can no longer communicate with the outside universe. And deeper inside, according to classical general relativity, everything eventually moves toward a singularity. But there is a problem. The mathematics stops being enough. This is why black holes are so important. They force physicists to confront the biggest unanswered questions in science. What is space made of? What is time made of? Is information truly preserved? How does gravity behave at the quantum level? And perhaps the deepest question of all, fundamental law. Does it emerge from something deeper? We don't have the final answer, but the search continues. New telescopes are observing black holes. Gravitational wave detectors are listening for collisions between them. Theoretical physicists are developing new ideas about quantum gravity. and every discovery brings us closer to understanding these cosmic objects. Perhaps one day, humanity will develop a theory that finally connects Einstein's gravity with quantum mechanics. When that happens, we may finally understand what lies beyond the event horizon. And that discovery could change much more than our understanding of black holes. It could change our understanding of reality itself. Because the most frightening thing about a black hole isn't that it can destroy a star. It isn't that light cannot escape. It isn't even that time and space behave strangely around it. The real mystery is this: black holes may be showing us that the universe is fundamentally different from the way we experience it. And somewhere beyond the event horizon, our current understanding ends. But the universe doesn't. It continues, silent, invisible, waiting for us to discover what comes next. Black holes are not simply the darkest objects in the universe. They may be the places where the universe is hiding its deepest secrets.